So as a group, you did very well, I think, on the quiz. So the results are just shown here. So the average was pretty high, a low A for the undergraduates and a strong A for the graduate students. So, but I did want to go over something that I think a lot of people missed. So E sub G, what we were looking for is the energy needed to free an electron from a covalent bond. That is different from the energy needed to break a covalent bond. Okay? To break a covalent bond actually takes more than 2 electron volts. Just to remove the 1 electron from a covalent bond, that's 1.12 electron volts, which is the energy needed to create a conduction electron and leaving behind a hole in the valence band. Okay? So for many of you who said break a bond and you didn't say anything about creating an electron, you got half a point off. Because there is a distinct difference between breaking the energy needed to break a covalent bond and the energy needed to free 1 electron from a covalent bond. Okay, but that was pretty minor. It's not really going to affect anybody's grade. But that was one thing that was missed quite a bit. I think that was it. I think pretty much you did very well. A few people, I guess, didn't realize that for holes, basically, these are electrons moving from one covalent bond to another, so it's best to have the atoms closely spaced together, so it's easy for an electron to move from one covalent bond to the next. So for hole conduction, you really have the best hole conduction in a plane that has the highest atomic density. Actually, more specifically, it's a plane that has the most covalent bonds lying in the plane, and that's the 110 plane. Okay? So the quizzes are sort of designed to help keep you keeping up with the fundamental concepts covered in this class. It's really to help make sure you are well prepared for the final exam at the end of the semester, which will count for the majority of your score in this class. Okay? Are there any lingering questions? I mean, it's good to learn before the quiz, but also after the quiz, just so that for the final you'll know everything. Any remaining questions from the exam? Okay. So one thing that I'm not sure in the homework that was just due, or the homework that's due next week, we're going to be asking you to draw band diagrams, maybe, or you already did draw band diagrams this time. But it's implied, but I forgot to point out explicitly that when you're applying a voltage across a junction, in equilibrium, the Fermi level is constant, right? The Fermi energy is at the same level in the metal and the semiconductor in equilibrium, so that there's no net flow of electrons, left or right from one material to the other. But when you apply a bias, when you apply a voltage, that equilibrium is disturbed. So the Fermi levels are split. So that's one way you can quickly tell by looking at an energy band diagram if the system is in equilibrium or not. So under forward bias, the Fermi level is split, right, between the metal and the semiconductor. It's not at the same level. And same thing for reverse bias. Okay, so this distance, oops, it's not really drawn clear, but the distance here, okay, the vertical split in the Fermi level energy is basically going to be given by the applied bias. Okay, and I'll leave it to you to figure out the polarity of the applied bias, but key thing is, right, this difference in Fermi levels is always going to be equal to, it's always going to be proportional to the applied bias. And qualitatively, forward bias means that the polarity of the applied voltage counteracts the built-in field, so the total potential barrier is reduced under forward bias. So you get exponentially more carriers diffusing across the junction. Under reverse bias, the polarity of the applied voltage reinforces the built-in field. So you get more voltage drop in the semiconductor. In other words, a higher potential barrier to carriers flowing into the metal. So basically, you block current from flowing, and the only current that flows across the junction is a small current flowing from the metal due to carriers flowing from the metal into the semiconductor. Okay, so that was a minor detail. But when you draw energy band diagrams, sometimes we'll ask you to indicate the applied bias on your energy band diagrams. And that's what's meant when I say that. Okay. Any questions left over from the metal semiconductor contacts? Yes. Oh yeah, Peng. Oh yeah. So I'm supposed to remind you or encourage you. If I think you all did pretty well on the quiz as a group, but if you feel like there's some concepts that are not so clear, we'd like to encourage you to take advantage of our office hours. I think we're a little lonely during the office hours. Or if they're not convenient for you, please feel free to send a message and ask for a special appointment. Okay, we're always happy to try to accommodate your busy schedules. All right, anything else, Peng? Oh yeah, discussion sections, yes. Right, so the discussion sections, Peng makes his PowerPoint presentation slides available online so you can look through them. He reviews and enhances what we cover in class. Okay. Okay, so today let's just talk about p-n junction diodes. So this is the next semiconductor device. So actually, I was thinking, does anybody remember what the university motto is? Go Bears. Like on the university seal, I mean, yes, let there be light. So I brought some p-n junction diodes. So here's an example. Unfortunately, not blue. But anyway, okay, so we'll have to pass this back to Camille since she answered it first. Can you pass it back? Anyway, so that's an example of a p-n junction diode. It's a light emitting diode. Okay, I'll ask another question later during class. Okay, but it'll take maybe like 3 weeks. I mean, the last lecture you'll learn how a light emitting diode works. Okay, it's actually made from 3,5 compound semiconductor material, but as long as you understand how a p-n junction diode works, you'll understand how a light emitting diode works. Okay, so in this class, we're really looking at integrated circuit devices. So, the p-n junction light emitting diode is not really an integrated circuit device, at least not yet. So I just wanted to mention, in an integrated circuit, we have a lot of transistors, and the transistors have heavily doped regions to form, let's say, the source and drain electrodes of a transistor. And the way that we form that is illustrated here in this slide. So we start with a wafer that's usually moderately or lightly doped. So let's say it's doped p-type. Then we form the source and drain regions by implanting, just basically shooting in like sandblast. It's not sandblasting. It's like shooting in like with a shotgun, like embedding these dopant ions into the surface of the silicon wafer. And then you have to heat up the wafer to like 1,000 degrees Celsius to heal the damage caused by that, shot of the donor ions in this case. So you get the donor ions you get the crystal to heal itself and to have the implanted donor ions reside on substitutional lattice sites so they can form covalent bonds with 4 nearest silicon neighbors. And then they can donate their electron to the lattice. So basically, in reality, in a p-n junction in an integrated circuit, at least one side of the junction has 2 types of dopants. But it's the dopant type that's dominant, the highest concentration, that would determine the type. Okay? So in this case, like what kind of atom or ion do you think we would have implanted to create this p-n junction? Arsenic or phosphorus, right? So you implant arsenic or phosphorus. Ions actually, okay, this is kind of confusing. So what happens is in order to give these ions kinetic energy to implant or embed themselves into the surface, they have to be accelerated to very high velocities. So that's the only reason why they're ionized. We have a source that generates these ions, and then they're accelerated by an electric field in this ion implantation system, and they hit the surface of the wafer. Once they hit the surface of the wafer, there's an electron gun that actually then attracts, because of the wafer will get positively charged, right? So what happens is then this electron gun will just provide electrons to the surface to neutralize it. So as implanted, the surface of the wafer is actually charge neutral, okay? But we have to ionize those atoms in order to give them kinetic energy to embed themselves into the surface of the wafer. So in principle, all you need to know is that we implant arsenic and phosphorus atoms. There's no net charge introduced by the implantation process. Okay. Now, once we form a p-n junction and we form metal contacts to the n-type and p-type regions, we can apply voltage. And if you apply voltage, you'll see a rectifying characteristic. Okay? So a p-n junction pretty much will always show a rectifying characteristic. You can't make it practically ohmic, okay? Not like a metal semiconductor junction. And the terminology is consistent. A forward bias means that you're applying the voltage with a polarity such that current increases exponentially as you increase the applied bias. And reverse bias is referring to the polarity of the voltage that's applied such that you have very little reverse current, current flowing. Okay? So just forward bias versus reverse bias. That's consistent with a metal semiconductor junction terminology. Now, one thing that's different in a p-n junction diode is that compared to a metal semiconductor contact is that we always define the applied bias to be positive with respect to the p side and negative with respect to the n side. So when you apply a bias, it's always higher. VA is positive if the voltage on the p side applied to the p side is higher than the voltage applied to the n side. Okay? So the IV characteristic, it turns out then, forward bias is always positive applied bias, and reverse bias is always negative applied bias with this, convention. Okay? And a circuit symbol sort of shows an arrow or a triangle with pointing kind of in the direction where current easily flows. And it has a straight line here on the left, sort of to indicate you're kind of blocking current coming in from the left. Okay, so as you know, in reality, when we form a p-n junction diode, there will be actually donors and acceptors on one or both sides of the p-n junction. In this class, just to derive the simple equations to tell you how the voltage is dropped across the junction and how current flows, we actually just ignore that. We just say, well, let's just assume that we have a p-n junction. The p side is doped only with acceptors to a concentration Na. And the n side is doped only with donors to a concentration Nd. Okay, so this is just to simplify the equations. Okay, so what this plot shows on the right is the net doping profile for a typical p-n junction. When we implant the surface, the concentration of dopants is highest at the surface, and it falls off exponentially as you go beneath the surface. That's kind of a realistic profile. And as indicated here, the metallurgical junction is just referred as the location, is referring to the location where the concentration of dopants of either type is equal. In other words, the net doping is zero. Right? Net doping is zero at the junction. Oops. All right, so So in this class, we're just going to focus on an ideal, what we call the ideal step junction. Okay, so this is what we're going to focus on. That's all you need to know, really, for your exams. Sometimes we give you a linear doping profile for a homework problem, but it's just a math exercise to rederive all the equations for a linear function of distance versus a constant function of distance. So I probably won't do that to you. But anyway, so in this class, we'll just look simply at a p-n junction. On the p side, we have a constant doping concentration of minus of Na. Okay, so the acceptors are negatively charged; they're ionized negatively, so they contribute negative charge density. And then on the n side, we only have to worry about the dopant concentration, donor concentration n sub d. Right, so this is minus Na, and this is plus. Just keep in mind, we're just actually ignoring the fact that there's dopants of both types on each side of the junction, just sort of writing equations as if there's only one type of dopant on each side of the junction. Now, so where is this going to really affect our estimations? Like what actually really truly depends on both types, the concentrations of both types of dopants? Mobility, that's right. So when you do your homework problems or the exam problems, if I tell you a p-n junction is doped, Na on the p side, you have to estimate like the minority carrier diffusion length, and to do that you need to know the diffusivity And to do that, you need to know the mobility. And the mobility, you're going to assume that's just Na, dopants on the p side. But in reality, it's actually going to be worse. Right? It's going to have Na plus Nd. But it's OK. So as long as you know that, that qualitatively would be a problem. We'll just keep the problem simple for you in this class. OK, so big picture is that when you have p-type semiconductor and n-type semiconductor, they start out with different work functions, or they always have different work functions. And when you bring them close together and touch, because they're different work functions, that means it's easier to move electrons from one material out of one material versus the other. Electrons will tend to flow across the junction and holes. And so you end up with some built-in electric field because you have charge going across on both sides. And therefore, you have some voltage drop across the junction. And in the end, if you have 0 volts applied, you end up with a constant Fermi level. OK, so this is an equilibrium. So if you go back to the website, I had it here. OK, if you look at the educational applets, what happens is, OK, on the left, OK, this is just an applet to show the formation of a p-n junction diode. OK, on the left, what do we have? N-type or p-type material? P-type, great. And on the right, there's N-type, right? Because the Fermi level is above the mid-gap on the right, so that's N-type. OK, so these are the energy band diagrams on the left and the right for p-type and n-type material. And when you form a junction, they touch. So you start out with a lot of electrons on the left side, not too many electrons on the right side. So when they touch, electrons will go to the right. And since you start out with lots of holes on the right and hardly any holes on the left for n-type material, when the junctions touch, the holes will diffuse to the left because of the concentration gradient. Oops. So let's see what happens. You touch. So as carriers diffuse, you build up, as mobile charge diffuses away, you leave behind a depletion region because you have ionized acceptors that can't move with the mobile charge, so they end up, so you end up forming a depletion region. On the right, you have, let's see, it's n-type on the right. So is this positive or negative charge on the right in the depletion region? Positive, that's right. Okay, so you have positive donors here, ionized donors on the right in the depletion region, and negatively ionized acceptors on the left in the depletion region in the p-type region. Okay, so in the end, the Fermi level is constant in equilibrium. But in order to get the Fermi levels lined up, you have to introduce some band bending. In other words, a voltage drop across the junction. Okay, so that's what's shown very quickly here. Right, so remember the electrostatic potential, goes, it's just negative. Okay, let's write that down. The static potential is just 1 over q times some reference level minus either your conduction band energy or your valence band energy or intrinsic Fermi level energy. It doesn't matter. Basically, this minus sign means that whenever V goes down, E sub C goes up. Right? So here's the, let's see, so, well, I should say the other way. If the electrostatic potential goes up, then E sub C comes down. It has the same shape, right? It's just opposite direction of curvature. Okay, the electric field is equal to the gradient of the electrostatic potential. And remember the Poisson equation? What is that? The rate dE dx equals what? Rho, so charge density, this is not resistivity, sorry, it's unfortunately confusing, but this is charge density in the semiconductor over the permittivity of the semiconductor. So on the left, we have negatively ionized acceptors, right, because this is the P side. And on the right is the N side. So in this class, just to be easy, we'll always draw the P-type side on the left and the N-type side on the right. So on the P side in the depletion region, you have some negative charge, and it's minus QNA on the P side. And on the N side, you have positively ionized donors up to a certain depletion width. So it's Q and D on the right. Okay, so the level of the charge density is set by the net dopant concentration, okay, ND and NA. So the slope here, is proportional to rho, right? That's what this equation states. And it's greater than 0 on the right, okay, because the charge density is positive. And slope here is, again, proportional to the charge density, which is less than 0 on the left, right? So it's negative slope. Okay, so qualitatively, so the charge density is a constant as a function of distance because the dopant concentration is considered to be, we're just going to assume it's uniformly doped on the p side, uniformly doped on the n side. So charge density is a linear, approximately linear function of distance, or sorry, constant function. And so the electric field is the integral of the charge density. So the electric field is a linear function of distance. So the electrostatic potential is a quadratic kind of function of distance. And so the energy bands, sort of have this quadratic curvature. Okay, so qualitatively, does anybody have any questions about this equilibrium electrostatics of a p-n junction diode? Okay, so let's derive an equation for everything. Okay, so what we want to know is this actually ultimately, we're going to use is the depletion approximation. So we're going to say that, okay, so within the depletion region, we'll assume that the mobile charge density is negligible compared to the dopant concentration. So we're just going to assume, all right, so let's say the charge density is going to look just like this. And outside of the depletion region, we'll assume that it's charge neutral. Okay, so the mobile carrier concentration matches the majority, well, the majority carrier concentration matches the dopant concentration. So that's on the n side and on the p side as well. Okay, so we're just going to assume that the depletion approximation holds for both the n side and the p side. And the width of the charge density profile, bless you, is going to look like this. So the width of the depletion region on the n side we'll just call x sub n, and the width of the depletion region on the p side we'll call x sub p. Okay? And what we really want to know is the depletion width, the total depletion width, W, which is equal to x sub p plus x sub n. Okay, so that's one thing we want to know. So what we have to do is just sort of assume, okay, there's a depletion depth x sub n on the n side, a depletion depth x sub p on the p side. We know that the total voltage dropped across the junction. Well, actually, we'll review that. But what is the total voltage drop? In other words, what is the built-in? When you have 0 volts applied, what is that built-in potential going to be? I mean, the difference, right, it's exactly going to cancel out the difference in Fermi levels that you start out with. In other words, it's going to be the difference in the work functions between the p side and the n side. Okay, so we know this if we know the dopant concentrations on the n and p side. So we know that. So basically, we can sort of take the integral of the charge density, get the electric field profile, integrate that to get the potential profile. We have the boundary conditions. It goes from 0 to the built-in potential. Then we can solve for the depletion width, and then we can solve for the peak electric field. Okay, so that's kind of the big picture here. Okay, that's basically what's described here. Okay, so let's derive the equation for the built-in potential, which, as was pointed out by Ali here, that's just a difference in the work functions. Bottom line is the difference in the work function on the p and n side. But if you look at this energy band diagram, hopefully you can see that this total amount of band bending here with 0 volts applied is the same. Okay, so E sub I is just drawn for reference here. It's near mid-gap. Okay, so remember the energy band gap energy is the same throughout this because it's just the same semiconductor material. Is just doped differently. So band gap stays the same. So the E sub I stays right in the middle of the band gap everywhere. So the total amount of band bending for E sub c is the same as for E sub v and for E sub I. Okay, so let's look at this total band bending for E sub I. Right, this is also QVBI. Does everybody see that? Okay, so if we look at that, we can see that that is equal to this distance plus this distance. Does that make sense? Josh?
EI is here below them.
Okay, all right. Yeah, some people answered the questions on the quiz really precisely. But anyway, okay, so the question that Josh was asking is, well, isn't E sub I slightly below the mid-gap? And the answer is yes, but it's so small we're going to ignore it for now. I mean, it still doesn't affect this equation that we're going to drive here. But you're right, it's like 6 milli-electron volts below the mid-gap. Okay, but still, even if EI is slightly below the mid-gap, these two green arrows still add up to the total band bending, right? Okay. Okay, so remember EF, this is P side on the left, and N side on the right, N-type dope side on the right. So on the left side, the difference between the Fermi level and the intrinsic Fermi level, you remember that simple equation, it's just related, it's just given by this equation here on the lower left. Yes, John. Huh? I'm Ross, I'm sorry.
Why is EI to EV the same?
Okay, so the reason for that is because the band gap is a constant for the material. It's all silicon, right? So all these curves, EC and EF, EC and EV, and EI are all parallel with each other. So the total amount of, yeah.
QVBI at the top is the band bending, right?
That's right. So the total amount of bending in this EC, that's the same as the total amount of bending in EI and the total amount of band bending in EV. Okay. Does that make sense? Sure. It's parallel. It's completely parallel. Okay. Right. Yeah. Sure. Okay. Does that make sense? Okay, so now on the P side, you have this familiar equation that relates that green arrow to, okay, so this is EI minus EF on the P side, right? And you have a familiar equation for the N side relating EF minus EI to the dopant concentration. Well, the carrier concentration, which we assume is equal to the dopant concentration. Majority carrier concentration is equal to the dopant concentration. Okay, so that's our always our simple approximation. Make sense? Okay, so let's add these two green arrows of these quantities together. Oops, maybe I intended to write it down. So let's just write this in. So QVBI, which is this, the sum of these two green arrows, is going to be equal to KT times the natural log. So it's KT times the natural log of NA over NI. Is that right? Plus KT times the natural log of ND over NI. But if you add logs together, it's the same as multiplying them together, right? Okay, so this is one equation to remember. Does that make sense? So hopefully this makes sense that the more heavily you dope, either the P side or the N side, the bigger the farther away the Fermi level is from the intrinsic Fermi level on each side of the junction. And so you're going to have a larger built-in potential. Okay, so qualitatively, why does that make sense? That if you have heavier doping on, let's say on one side, let's say you have a PN junction and you increase the doping on the P side. Why does it make sense that the built-in potential should be larger? That's a very complicated but correct answer. All right, let's give you a p-n junction. Okay, so I like to think of it as you have more concentration gradient, right? You have heavier p-type doping on one side than the other. So basically, you end up with a higher concentration gradient. So what happens is when you make the p-n junction, you have a concentration gradient, so the carriers diffuse across. But then what builds up is a electric field that creates a drift current that counteracts that. And at equilibrium, it balances out, right? Drift and diffusion balance out in equilibrium. So if you have a larger concentration gradient to start out with, you need more drift current to just hold it back, right, to balance it out. So you need to have more built-in potential to hold back the drift current. That's kind of, I think qualitatively, that's what makes, it might be easier to remember than your correct long answer. Okay, now usually in a transistor, you're going to get tired of seeing the transistor by the time we get to work on the transistor. Usually in a transistor, the source and drain regions are very heavily doped. They're usually degenerately doped. So in an integrated circuit, it's quite common, and then for a p-channel transistor, you have heavily doped p-type regions with a lightly doped n-type body. But in any case, it's quite common in an integrated circuit to see one side doped much more heavily than the other side. Okay? And one side could be doped so heavily that it's degenerately doped. So remember, what's a degenerately doped semiconductor? Do you remember? Yeah, right, EF, okay. And so just for simplicity, where do we assume the EF is for a degenerately doped? Exactly. Yeah, I was telling Peng this semester, you guys seem to be much smarter than in the past. So that's great. No, it's a really bright group of students this year. That's great. So multiple people said the right answer. I'll bring more pens next time. But p-n junction, okay, so basically then, remember the equation on the previous slide, the way we derived this simple equation that's easy to remember, but it only holds if both sides are not degenerately doped. If one side is degenerately doped, okay, it's rare to have both sides degenerately doped, so don't worry about that. But if one side is degenerately doped, we actually cannot use one of these equations, because one of these equations were both derived using the Boltzmann approximation, which only holds for non-degenerately doped material. So instead of using one of these equations to determine the difference between EF and EI, we just use 1/2 the band gap. Right? The side that's degenerately doped, we assume the voltage drop, the Fermi level minus the intrinsic level is 1/2 the band gap. Okay? So let's just do this, make sure I don't make any mistakes here. So for P plus silicon, EI minus EF is equal to, and I realize I'm sure somebody's going to say, yeah, with degenerate doping, you're going to have a narrower band gap and so on, right? Band gap narrow. So we'll ignore that. So just assume it's just 1.12 at room temperature, 1.12 EV divided by 2. Okay? Just keep it simple. So for P plus silicon, the Fermi level is just right there, okay, at the band edge. So this little green arrow is now going to be EI minus EF, which is EG over 2. Okay, so the built-in potential is going to be EG over 2 plus KT times the natural log of ND over NI. Okay? So this case is actually more common than not. And then for N plus P junction, let's just be complete. For N plus silicon, EF minus EI is equal EG over 2. So the built-in potential, so I'm just saying that, but it's QVBI, right? So built-in potential has units of volts. Energies are electron volts, so you have to multiply by Q in front for the units to work out. So this will be KT times the natural log of NA over NI plus EG over 2. Okay? Have any questions about this not so uncommon case of one side being degenerately doped? Okay, so now we have a simple equation to give us the built-in potential. So now we can work backwards and start with a depletion approximation to come up with an equation that describes the potential versus distance and apply this boundary condition to solve for the unknown, which is the depletion width. Okay? Okay, so the depletion approximation, on the p side, the charge density is just going to be equal to dopant concentration times the charge of each of the dopants, which is minus q. Okay? So from Poisson's equation, we have the derivative of the electric field is equal to the rho over epsilon s, which is equal to minus q na over epsilon s. So if we integrate that constant function, it's just going to be a linear function plus a constant as a general solution. Okay, and so one boundary condition that we can set here is the electric field strength at the edges of the depletion region. Basically, there should be negligible electric field in those charge neutral regions. Okay, like there's no reason to have electric field in those regions. So we can actually set this equation for electric field to be 0. So this is equal to 0 at, what are we going to do? X equals, at minus xp. Let's start there first. So the electric field at x equals minus xp is equal to 0. Okay, so that means that C1 is 0. Oh, sorry. I'm sorry. That's wrong. That. Okay, I mean, okay. Actually, then you can solve for C1. Let me just write this down. So you can solve for C1. And it turns out then, if you simplify the expression, that you end up with this formula for the electric field on the p side. Okay, so you can see easily that if x equals minus xp, this expression goes to 0. Okay? And it's an exponentially decreasing, it's a linearly decreasing function with distance. And the slope is equal to minus q na over epsilon s. Okay? So similarly, on the n side, you can apply, again, Poisson's equation. So that's dE dx, the electric field, is equal to q nd over the permittivity of silicon. And again, the electric field at x equals x sub n is equal to 0. So that is how you solve for the constant here. And so you can see from this particular solution that if x is equal to x sub n, then the electric field is 0. Okay, so it's a linear function of distance x, and it's actually decreasing in magnitude. Actually, it's becoming less negative as you go to positive x. And so the slope is a positive slope, as I mentioned on the previous slide. Okay, so n sub d, oh yeah, sorry, thank you. This typo, n sub d, thank you. So we know that the electric field, okay, is 0 out here in the quasi-neutral. So we call these the quasi-neutral regions, or the neutral regions. Electric field 0. And so from the equations on that previous slide, you know, it's a linear function of distance, at least based on the depletion approximation. And it should be continuous at the junction. So the electric field looks like this. Right? So you have positive slope on the right because the charge density is positive, proportional to n. And you have negative slope on the left, proportional to so actually just for conservation of charge, you know, when you had started out with P and N-type material, there's no net charge anywhere, right? So if you actually have charge flowing across, mobile charge flowing across this junction and leaving behind negatively charged and positively charged ions on either side, basically the total charge on the right in the N side has to equal in magnitude to the total charge on the left on the P side. So that's what this equation states, right? NA times X sub P is equal to ND times X sub N. Okay, actually, well, this can be derived from Poisson's equation as well, if you integrate it on both sides. Okay, so now we have the electric field distribution. We can integrate that again and get the electrostatic potential as a function of distance, and then apply the boundary condition that we know to be the case. The total built-in potential is just VBI. Okay? Okay, so I think that's why we wrote it this way. Okay, so let's look on the P side. It's this constant, proportional to the dopant concentration, times the quantity X plus X sub P. So now if you integrate this electric field expression, you get X plus X sub P quantity squared over 2, right? That's what we have here, right? That's just the integral. And then you have to add a constant for the general solution. Okay? But let's define, remember electrostatic potential is all relative. So we'll define the electrostatic potential to be 0, so that's a reference, at x equals minus xp. So in other words, we'll define the electrostatic potential, I guess somewhat arbitrarily, but not really, to be 0 at the edge of the depletion region on the P side. Okay, so let's draw that. So this is distance, x sub n on the right, the depletion region, extension to the N side and to the P side. So we're just going to assume, we'll just set electrostatic potential to be 0 on the P side, like right here. So we're just going to say, okay, let's assume the electrostatic potential is going to be, there's no electric field in the quasi-neutral region, the P-type region. So there's going to be no voltage drop or negligible voltage drop in the quasi-neutral region. And the potential will be 0 right here at the edge of the depletion region. Okay, if that's the case, then what is D1? Okay, if you plug in x equals minus xp, yeah, it's 0. Very good. All right. Okay. All right. So then you have the simple equation for the voltage, the electrostatic potential as a function of distance. Okay, so the other boundary condition we want to set is that we reach the built-in potential at the edge of the depletion region. So basically, we know the total voltage dropped in equilibrium across the depletion region is the built-in potential. So it has to go from 0 to VBI across the depletion region. The question is, what does it look like? Okay, so what shape is, if you look at V sub x, this expression for V sub x, what should I be drawing here? Yeah, that's right. Sort of concave, is this concave? Concave up. That's right. Let's draw a gently increasing concave up kind of a curve, right? So it'll look like that. That's right. And then on the N side, you know that this, okay. Well, what is D2 if we know that at x, V at xn is equal to VBI? Right. So D2 equals, my computer's just like hyperactive. Okay. D2 equals VBI. Very good. Okay, so Xue already mentioned this equation is a quadratic, but it's going to be concave downwards. Okay? So at the metallurgical junction, you have an inflection point, right? Changes from concave up to concave down at the metallurgical junction. Now, for the homework that's due next Thursday, you have to be a little bit careful because, well, as we'll derive, if the N and P side are not symmetrically doped, if they have different levels of dopant concentration, then because of this equation here, like if Na is much, much greater than Nd, then Xp will be much, much smaller than Xn. And so if that's the case, okay, I'm just going to draw that, sketch that here. So what if Xp is like here and Xn is like out here? If one side is much more heavily, if the P side is much more heavily doped than the N side, then you have this concave up going right here, and it'll be mostly concave down. Right? So you're not going to have a symmetric, band bending. I mean, most of the voltage will be dropped across the N side. Okay? So that's a detail that you should actually pay attention to when you draw your band diagrams. Okay? So most of the band bending occurs on the more lightly doped side of the PN junction. Okay, so let's derive an equation for the depletion width now. At x equals 0, okay, so at x equals, oh, I don't know what's going on. At x equals 0, this expression on the N side has to equal this expression for the P side. Okay, so let's just set those two equations equal to each other at x equals 0. Right? So if x equals 0, you just have xp squared on the left and xn squared on the right here. Okay, so I'm just going to do that. Qna over 2 epsilon s times xp squared equals vbi minus qnd over 2 epsilon s xn squared. Okay, so we have one equation for xn and xp. We don't know what either of them is, so we need another equation. We need two equations to solve for two unknowns. And we assume that Na and Nd are given to us, are known. Okay. So we can write, for example, we can express xp in terms of xn. Right? Then we can plug this equation for xp back in to the equation on the left, on the top to the left. Okay. And if we do that, we can solve for xn. Okay. So that's how we eliminate xp and we can get xn. Or you can write xn is equal to Na over Nd xp, right? Then you can plug this expression for xn into the equation on top and solve for xp. Okay, if you do that, you get this middle equation on this slide. Now, if you add those two together, we get the total depletion width, and basically this is the answer right here. Okay. Okay. So fortunately, well, so this is good to remember, but fortunately, usually, like in an integrated circuit, one side is much more heavily doped than the other. So one of these terms is going to be much smaller than the other. So typically, then, what term do we keep in this parentheses? Which term is actually going to be the dominant term that and we can neglect the other one? Minority. Yeah, so okay, so the side that's, what? The side that's more lightly doped, do you think we can throw away that term? No. No, it's the opposite, right? So you throw away the term associated with the more heavily doped side. Right? So let's say if the P side is more heavily doped, you would throw away this term, right? Because 1 over Na would be much smaller than 1 over Nd. So that's right. So that's what's shown here as an example. If the P side is much more heavily doped than the N side, we would call that a P plus N junction. That's just to indicate that the P side is much more heavily doped than the N side. Then we can just say the depletion width is just going to be inversely proportional to the dopant concentration on the N side. Okay, and x sub n is going to be much greater than, right, because NaXP is equal to NdXn. So if Na is much greater than Nd, then Xp must be much smaller than Xn. So most of the depletion region is on the N side, so the width of the depletion region is approximately equal to x sub n. Okay? What about this hopefully is trivial for you. But anyway, so what about an n plus p junction? You can write 1 over Na plus 1 over Nd is approximately equal to what? All right, 1 over Na. So yeah, so basically, it's just going to be same as this equation up here, but you have QNA. So bottom line is you just have to remember it's just going to be inversely proportional to the dopant concentration on the more lightly doped side. That's basically what is summarized here at the bottom. Yes, Andrew.
Okay, so let's say you can create that be like the logical simple.
Okay, so the question is there a benefit to having a larger depletion region for a PN junction? Yes. Or they can be. It depends on the application. Okay, that's a good question. So let's think about, okay, I can always go back to the MOSFET, but let's say for a PN junction, okay, if you want to have, let's say, a PN junction serve as a photodetector, like a light detector, right? So what happens when you shine light on a semiconductor? You generate electron-hole pairs. And if there's an electric field present, then electron and hole will be swept away in opposite directions. They'll be separated, and they can go out through the terminals, right? So they can generate current. So if you want a PN junction diode, okay, let's go back up here. Okay, so here's a PN junction diode at equilibrium. But if you shine light on it, okay, so if you were to generate an electron-hole pair because of light absorption, you have a hole here, an electron here that's generated due to light. So electron will want to drift to the right, and the hole will want to drift to the left, and they can flow out the metal contacts, generate current. Well, I mean, so you can detect it. Your circuit can detect light shining, right? So photodetector. So if you want your photodetector to be more sensitive, then you want to generate more electron-hole pairs. So you want the depletion region to be wider, so more volume of light generated. Okay, that's one example. For a MOSFET, actually the depletion region, okay, so most of the depletion region is going to be on the more lightly doped side. Actually, that's not good because if the depletion region, let's say, of the drain, the transistor actually reaches across the short channel, the short distance, just tens of nanometers, and touches the source junction, then you basically have a punch through, what we call punch through. So carriers can easily flow between the source and drain out of control of the gate. So that's actually bad. So for a MOSFET, we actually don't like to have a wide depletion region if we want to make very short channel MOSFETs. So depending on the application, you want to have either a wide depletion region or a narrow depletion region. One thing is, to change, if you want to apply a voltage to a PN junction, you do have to change the charge stored, just like a metal semiconductor kind of, you have to change the charge stored. So there's some capacitance. And the capacitance depends on the thickness of your depletion region, or the width of your depletion region. The narrower the width, the higher the capacitance. So from a power consumption standpoint, actually, it's not good to have high capacitance. They have to charge and discharge to change the voltage in your integrated circuit. So for that reason, you actually don't want a very narrow depletion width to save power, lower capacitance, a small signal capacitance. So we'll go through that slowly in the coming weeks. Okay, but it's a good question. Okay, so I don't know if we have an example, maybe not, but okay. Just order of magnitude, typically a depletion width is on the order of, it depends on the doping, right? The doping can change over many orders of magnitude. In an integrated circuit, it'd be 10 to the 16 up to maybe 10 to the, on the lightly doped side, could be 10 to the 15, 10 to the 16, up to 10 to the 18, mid 10 to the 18. So it's orders of magnitude. So the depletion width can change over more than one order of magnitude, but typically it's on the order of a tenth of a micron. Okay, so anywhere from hundreds of nanometers, no, many tens of nanometers to hundreds of nanometers. So it's usually less than a micron. Okay, now if you have a photodetector, then you might purposely make it more than a micron. Okay, but order of magnitude, just when you're doing your homework. If you're getting a centimeter or something, that the answer is way off. Okay. Okay, so let's see. What is that peak electric field strength? Oh yeah, that's reminded me. So let me go back. Sorry, this is a non sequitur. actually, it's interesting. In integrated circuits today, we're fitting more and more transistors in a square centimeter. So not only is the size of the transistor shrinking, but the size of the little contact holes, where you have a wire coming down and touching the semiconductor, is shrinking. So it turns out in this example that I gave you, so this is actually a real problem today, because we actually are starting to have so much current flowing in a small area. The current density is high. We're starting to see some reliability issues with the metal interconnect. Right? Okay. So the example I gave you actually was like too much current flowing through this small. So if a contact hole is that small, we wouldn't really flow a milliamp through it. More practical is like 1/10 of a milliamp. So the voltage drop typically then, for a reliable circuit operation, is going to be 10 millivolts rather than 1/10 of a volt. So 10 millivolts is negligible compared to like a typical operating voltage of 1 volt. So that's why we can sort of make the assumption that the voltage dropped across an ohmic contact is negligible. Okay, and therefore the excess carrier concentrations are essentially 0 at an ohmic contact. Okay. Anyway, I forgot how I got on that topic, but we'll go back. Okay. Oh, yeah. So yeah, electric fields. We can actually start to approach, in the modern integrated circuits, can actually approach, can be very high and approach a breakdown field of the material. So it is interesting or important to keep track of, how high is the electric field at your junction, because if it's too high, your junction will break down, and we'll talk about that maybe next week in terms of the breakdown phenomenon. Okay, so let's go back and sketch the electric field versus distance. And remember, it looks something like, it was a triangle, right? Okay, so if the P side is doped much more heavily, than the N side, so let's just say it's a P plus N junction. In other words, the P side is doped much more heavily than the N side. Which side, again, is going to have all the voltage drop? The right side, right? The N side, the lightly doped side. And the electric field, therefore, will be primarily on that side. So let's change color here. It's going to look, okay, I guess this might be a little exaggerated, but basically, minus x of p, it's close to 0 on the same linear scale. Okay, so here's the electric field at 0, x equals 0. Okay, so remember the slope of electric field. Slope is proportional to minus NA, right? And if you say NA is much greater than ND, then that's why it's much steeper, right? Steeper negative slope on the left side versus the right. But the electric field is continuous at the junction, so that's why the width of the depletion region is so small, negligible on the heavily doped side. Okay, so it just looks like a right triangle. So you can use the equation for a right triangle, right? 1/2 times the height times the width of the base, and that's essentially what that is. And the integral of the electric field, at equilibrium is just a built-in potential, right? So that's what right here. So 1/2. So the area of this triangle is just equal to the built-in potential. Then we can solve for the depletion width. We already kind of did that on the previous slide. But now we can have an equation for the peak electric field. And that's not too surprising. I guess it's just, the change in voltage. I mean, electric field fundamentally, let's see. Electric field is just the change in voltage with a change over distance. So you drop VBI over W, right? The total voltage drop is VBI. The distance across which you drop it is W. So the peak electric field, interestingly, increases with the dopant concentration. Okay? And ideally, it should be less than about a megavolt per centimeter if you want to avoid junction breakdown. But we'll cover that next week. Okay, so let's just go back. Okay, so remember we talked about this. I don't know why this keeps disappearing, but concave up on the P side, concave down on the N side. So for a P plus N junction, as I already sketched and it was erased, let's see what that looks like. Again, let's just draw it one more time. it's going to, so most of the voltage, so we know it has to go up to VBI on the N side, and it starts out at 0 on the P side. So since all the band bending and the voltage drop is on the N side, it's just going to be concave up like this. Okay, so qualitatively, okay, so if on a quiz or a final exam you're drawing energy band diagram, do not draw this, and don't draw this if it's for a P plus N junction. Okay, you have to make sure that the curvature is correct in your your exam answers. Okay? So bottom line is, if you go back and look at the equations for electrostatic potential on the P side and the N side and equate them at 0, you get this expression. So basically, this means that most of the voltage is dropped across the more lightly doped side. So if you just like looking at equations, okay, if NA is much greater, if you just look at that equation, if NA is much greater than ND, what does that equation give you? V at 0. NA is much greater than ND. Close to 0, right? Okay, right, because if then this would become negligible compared to NA, and this ratio is very small. So that's what's shown here, right? V0 is approximately 0 for this P plus N junction. Now, conversely, if ND is much greater than NA, okay, what will it look like? If we have PN plus, we know it has to reach VBI at XN. Oops. Well, hold on. XN, okay, so first of all, XN is much smaller now, right, than XP. XN is like near 0, and XP is out here. So what is this going to look like? It is concave, but which way? It's going to look like this. Okay? So when you draw the energy band diagram, you just, you flip the, flip V sub x to get the, energy, the E sub C or E sub V. Yeah. Okay, so the key is that, the voltage is dropped on the lightly doped side. So it's on the P side here on the bottom, and it's on the N side in the other example towards the middle. Okay? Questions? Oh, great, we get to do an example. So you get an idea of the order of magnitude. Oh, good, I have the answers. Okay, so let's say this is a P-type, heavily doped on the P side and moderately doped on the N side. Let's just go. So what is this first term here? 56. 0.56 volts, right? And 1/2 the band gap divided by Q. So you get rid of the E. So it's 1.12 EV divided by 2, and then you take away the E because you're dividing by Q. Okay, and then what is the second term? Great. 0.42. So this is 0.98 volts. So it's approximately 1 volt. So the PN junction built-in potential is typically 1 volt, close to 1 volt. Okay? How does that compare with a Schottky diode? Typical built-in voltage. Much higher. You're right. Okay. Okay, that's good. Keep that in mind because I might come back to that. All right, so the depletion width, since one side is much more heavily, is a one-sided junction, we can just worry about the doping on the more lightly doped side. Okay, so let's just write, I'll just write in the numbers. So it's 2 times, okay, so epsilon sub s is just want to remind you, and then we'll provide this to you in the exams. But basically, it's easy to remember, well, relatively easy to remember. If you take 11.7 times 8.854 times 10 to the minus 14, okay, you get 10 to the minus 12. Okay, so just epsilon sub s is just 10 to the minus 12 farads per centimeter. And then VBI, let's just assume it's 1. Take the square root over Q, which is, oops, I hope you remember Q is just 1.6 times 10 to the minus 19, and then 10 to, ND is 10 to the 17. Okay, so who can do this in their head, I hope? It's not that hard, right? I mean, very roughly, right? So on the denominator, you have 10 to the minus 2, and the numerator. Okay, so this whole thing in the parentheses, it's very roughly 10 to the minus 10 to the minus 10, very good. And then so the solution is close to 10 to the minus 5, right? So 10 to the minus 5, what is, oh yeah, so very few of you forgot to write units on your answers in the quiz, so that's minus half a point. And so the units are important, right? Because how do you know? What is this? 10 to the minus 5 meters, 10 to the minus centimeters, very good. And what is that in terms of microns? 0.1 micron. Okay, so as I said, the typical depletion width is on the order of a tenth of a micron. Now for a transistor, as I said, you don't want that depletion width to punch, go all the way across the channel. And if your channel is like 30 nanometers, then that tells you that that channel region must be more heavily doped than 10 to the 17. And it is. It's like over 10 to the 18 today. Okay, so that gives you an order of magnitude, about a tenth of a micron. And it's mostly on the N side. On the P side, okay, so this is about 0.1 micron. How much is the depletion region on the P side? Okay, approximately 0. But if I wanted to ask, like, for a precise answer, what would it be? Yes, it's about 1 angstrom. That's pretty small, right? So that's why we can say, oh yeah, it's negligible. Okay, so all this voltage is dropped. All the energy band bending occurs on the lightly doped side. Very good. Okay, so next time we'll talk about deriving the current versus voltage equation, but just qualitatively, again, if you're applying, okay, so we're assuming ohmic contacts now to the P side and the N side, far away from the junction, and we're assuming that, okay, so we know that current, okay, if you apply a voltage, current is going to flow. Let's just draw it this way. So current will flow in response to that applied voltage. And that current will flow, and it'll be constant. So no matter if you're looking in the P side or in the depletion region or the N side, the current flowing through those regions is going to be the same. Right? They're all in series. Okay? But there's going to be some resistance, right? Because it's doped material. There's going to be some resistance of the P region. There'll be some resistance of the N region. And the depletion region effectively, you can think of it as going to have some impedance, some resistance to current flow. Okay? Now the depletion region doesn't have a lot of mobile charge carriers. So again, where is most of the voltage going to drop when you have the same current flowing through all three of these resistors? The depletion region, right? Because the depletion region effectively has the highest impedance. These doped regions are going to be electrically more conductive than the depletion region. So when we apply a voltage to the p-n junction, we're just going to assume the main thing it does is it changes the voltage drop across the depletion region. Okay? Okay, and one thing in the past, so the applied bias, so that built-in potential, okay, let's see, let's go here. So at equilibrium, you can tell it's at equilibrium because the energy band diagram shows the Fermi level is constant, okay? But as you apply a voltage, the Fermi levels will split, okay? And it doesn't matter if it's positive or negative bias. I mean, in terms of the magnitude of the difference in the Fermi levels, the split in the Fermi levels will just be the applied bias. And so this built-in potential, the voltage drop across the semiconductor or across the junction will be reduced under forward bias by VA, and it will be enhanced under reverse bias. Okay, so VBA is negative under reverse bias. So this magnitude here under reverse bias, this is reverse bias down here, increases. Okay, so let's see, multiple things are happening here. If you change the potential barrier height, then you will actually make it easier for carriers to diffuse across the junction. You know, exponentially more carriers have enough kinetic energy to go across the junction in either direction. Electrons from the right to the left, holes will diffuse from the left to the right because of the concentration gradient. Under reverse bias, well, the diffusion currents are going to be, there'll be very few carriers that have sufficient kinetic energy to go across, to diffuse across. And so the only current that flows is just some very small drift current. But in any case, today we're just focusing on electrostatics. So the width of the depletion region will have to shrink if the total voltage drop is reduced. And the width of the depletion region will have to grow to drop more voltage across the depletion region. Okay, it's just because, you know, Poisson's equation integrating to electric field and integrated electric field to get the total voltage drop. So if the total voltage drop increases, the only way to increase the voltage drop across the junction is to make the depletion width wider. Okay. Something I was going to say here, but anyway, any questions in the short term? Oh, yeah, what I wanted to say was, when you reduce this, when you apply forward bias, we're going to talk about 9 ideal effects in a couple of weeks. It is never practically possible to completely eliminate that potential barrier. Okay, because as you decrease that potential barrier to diffusion of carriers across the junction, the current density will grow, and the diode will heat up eventually, and it'll melt before you can actually reduce that potential, you know, barrier to zero. So just keep in mind that the potential barrier can never be reduced to zero in practice. There's just physical limits. Okay, so what's one easy way, if you look at the energy band diagrams, what's one easy way to tell if we're looking at a diode, okay, first of all, in equilibrium. That's really easy, right? Fermi level, very good. And then if the Fermi levels on the left and right side, oh, I forgot to point out, now we're starting to use this notation, E sub F sub P. That's the Fermi level in the neutral region on the P side. E sub F sub N is the quasi-Fermi, it's not the quasi, sorry. It is the Fermi level in the neutral region on the N side. Okay, so that's different from the quasi-Fermi levels. That's why I'm getting confused. Okay, so that's just a little bit of new notation. Okay, so just looking at, let's say, this bottommost energy band diagram, how can you tell that whether or not it's forward bias or reverse bias? Just qualitatively, just looking at it. Okay, somebody raise your hand. I have no prizes to give out. Okay, how about in the back? Yes. Okay, P-type Fermi level is higher than N-type Fermi level. So you have to, that requires some thought like, okay, what polarity of voltage is being applied? So it's a little bit complicated. If you're under stress on a test, you might not be able to remember that. So I'll give you a hint. The built-in potential, note, maybe not, okay, note that the built-in potential, or Q times the built-in potential, is always going to be less than the band gap energy. If you think back to the equation for the built-in potential, let's go back. Right? If the built-in potential is equal to the band gap, that's the largest you can get, that means like both Fermi levels are at the band edges. Right? That means both sides are degenerately doped, which I told you never in practice is the case, and we'll talk about why later. Basically, you get tunneling, quantum mechanical tunneling. It's not working as a proper diode anymore. Okay, so that gives you a hint. The built-in potential is always going to be smaller than the band gap energy. Okay, so all you have to do is look at the total amount of, like, look at this potential barrier, right? What is the total band bending here? Is it greater than or is it less than the band gap energy. It's greater. So you know this has to be under reverse bias because the potential is somehow more than it can possibly be at equilibrium. Okay? So that's a quick way to recognize when I give it to you on a quiz or final. Okay, if I ask you, okay, which one of these is forward bias, which one is reverse bias, rather than thinking, okay, plus, minus, figuring out which direction the electric field is pointing and which polarity the applied bias is, just look and see, is the total potential drop greater than the band gap energy? If it is, then it's got to be under reverse bias. How about in the middle now? See, the total potential drop is clearly much smaller than the band gap energy, and typically the built-in potential is kind of 1 volt, so it's close to the band gap energy. Okay, so does that make it easy for you to? So if some professor in the future gives you a trick question and switches the p and the n side, so you don't have to worry about the polarity being switched. Just look at the magnitude of the band bending relative to the band gap energy. Okay. When we talk about BJTs, we're going to have PNP junctions and NPN junctions, and you're going to get all, P will not always be on the left, and N will not always be on the right. Okay? All right, great. I think that's it. If any of you haven't picked up your quiz, please come up to the front, and have a nice weekend.